Hi, in this video I'm going to show how to use a reinforcement learning for the cruise control of a vehicle in this simplified Symbolic model. The cruise control is going to search to obtain the velocity set by the user in addition to maintain a safe distance relative to the lead car, to the car in front of it. Okay, a reinforcement learning is a learning technique in which an action is taken based on the observation of the environment and a reward. The reward can be positive or negative depending on how you program. I'm gonna go in detail into that. Okay, so the agent will have a deep learning neural network that predicts the long-term reward based on this observation and data that takes as input. Also, it's going to have a deep learning neural network to predict the new action that it's going to take on the system. So the action is taken, then you have a simulation environment that predicts how the car is going to behave, and then you get the observed data, which could be the position, velocity, and on that you get a reward, which is a formula that you establish, and then from that the reinforcement learning agent is going to predict the next action, and that's going to be the acceleration in this case, or it could be a force or any action that you can take on the system. Okay, let's take a look at this example. We're going to open it by clicking here. Okay, that takes us here, and first we're going to set some parameters. One of the most important is the initial position of the car in front, and also the initial velocity of that car, and also the velocity and position of the car that we're trying to control. Everything in meters and meters per second. We're going to set the default distance, the spacing between the cars. Understand that it should be 10 meters. And also the time gap, and the time gap is going to be used to multiply against the velocity of the ego vehicle to compute, and it's added to this one. So it's something like a velocity ego multiplied by t gap plus the default is equal to safe distance. So these variables are used for that, and this safe distance is subtracted by the relative distance. The relative distance is x ego lead minus x ego. So the difference, so basically you want that the distance between the car in the front and the car in control is below, is above the safe distance. So yeah, so yeah, I think it's in the opposite direction. Or something like that. If this is negative, then you're good because your difference is higher than the safe distance. So we're gonna see this in the model in a moment. Okay, so the only thing in this model, the only thing that we can control is the pedal of the car, the acceleration. So we're gonna limit that between -3 and 2 meters per square seconds. So that's going to be our acceleration limits, and we're going to use a sample time of 0.1 with a final time of 60 seconds. This is going to be the model. We're going to open the model, and we're going to have a reinforcement learning agent block, and at the beginning it's going to appear in red because we haven't defined it, and you can see the name RL agent. So we use the model path. We're going to need this to create the environment. So you notice that this is the name of the model and the name of the block. This is the format to specify the path of a block within the Symbolic model. Okay, so let's take a look at the model. So it is we have to model both the control and the environment in the Symbolic model. And the environment is basically consists of the ego car and the lead car. It is very simple model. We have the initial position, the initial velocity, and the acceleration of the lead car is going to be a sine wave. So inside of it, we can see the acceleration is just integrated to get the velocity, and then add the initial velocity. And once we have the velocity, we just integrate it again, get the actual velocity, and once we integrate it, we have the position, and we add it to the initial position and go on. Okay, so it seems that the car it goes accelerated back and forth because of this sine wave. Okay, so in the ego car is exactly the same. We get the acceleration, the initial position, and initial velocity, and we're gonna integrate it to get the velocity, add the initial velocity, integrate again to get the position, and add to the initial position, and then we get the actual position and the actual velocity. Okay, so all these measurements of the are going to be fed into here, and notice we give the velocity of the car, we give the velocity of the lead car, but then for the distance we get the relative distance. That is the difference between the car in the front and the car in control, the ego car. So if this distance relative is negative, it means that your car hit the car in the front, which is not good. And also we're going to provide the acceleration as part of the computation of the reward. This is important because we don't want to accelerate too fast or give a rough acceleration. Okay, so I think I missed a variable. I'm gonna make sure that I have it. Yes, effectively, I missed creating the VSET. That's why it was in red. Okay. Now it's not red anymore. Okay, good. Okay, so in here we compute the reward. This is how you program the reinforcement learning. You have to set the rules for it. But before going there, we're gonna see how the distance error is computed. So the safe distance is computed here, and it depends on the velocity of the ego car, the car in control. So as mentioned before, the velocity of the car is multiplied by the time gap, and that is added to the distance default, and that determines your safe distance. And the safe distance is subtracted from the distance, a relative distance between the lead car and the ego car that is computed here. And that's the relative distance. So yeah, so you subtract the safe distance minus the relative distance, and we're gonna feed it into here, and here we're gonna compute the velocity error. The velocity error is gonna give you, so you want to bring down to zero that velocity error, which means that you want to get into that selected velocity. So we're gonna see how that velocity is selected. Okay, so we feed the velocity of the ego car and the velocity of the lead car. Once we go in here, what's going to happen is that we're going to have a switch, and the decision of the switch has a threshold of 0. So if the error is below 0, you're going to go through this path. What does it mean that the velocity is below 0? Velocity below 0, the error below 0 means that this number here is negative, and it is only negative if the relative distance is above the safe distance. So by having a negative error, it means that you're safe, you're beyond safe. So if you're beyond safe, you don't care anymore about the car in the front, so you're gonna care about getting into the velocity set by the driver. So it's gonna be, for example, 30 meters per second. So this is when it's gonna appear here, and you're gonna subtract that 30 meters per second by the velocity of the ego car. So you're gonna try to minimize this and get into this velocity. Okay, now if the error is above 0, it means that you're not in a safe position. So what's gonna do? It's gonna take the velocity of the lead car, and if the velocity of the lead car is below the velocity set by the user, it's gonna try to get into the velocity of the lead car. Yeah, I don't know if this is the best way to do it, but at least it's gonna try to get it's gonna try to increase the safety, the distance between the two cars. But if the velocity set by the user, by the driver, is less than the velocity of the car in front, then it is okay to follow it, because the car is getting farther and farther, so eventually the safe distance is going to be there. So that's why it can select this as well, even though you are not in a safe distance. Okay, so now that you have the velocity error, that is going to be used for the reward, but also it's going to be used for the observation. The observation is part of the data for training of the agent. for determining the next action. So you only get the velocity error, but also integrate the velocity error, and also provide the velocity of the ego vehicle as part of the vector, which is an array of 3 elements that is provided as the observation vector. Okay, so now let's go to the reward. The reward takes the acceleration of the vehicle, of the ego vehicle, and that acceleration is the previous acceleration. So you can see here that it is the previous acceleration. So, and the velocity error. Okay, so notice that the output is a scalar, and the scalar is multiplied by -1, which means that we're going to have a sum in here. So everything that is positive is going to become negative, and you want to maximize the reward. So basically, the negatives in here are like sticks. You want to train an animal with sticks and carrots. So the negatives are going to become the sticks, and the positives are going to become the carrots. So the only carrot in here is this one. And the carrot happens when the velocity error is below 0.25. So it means that you're close to the velocity, and that's all you want to get. The velocity could be the velocity set by the driver, or it could be the velocity of the lead car because you want to increase the safe distance. Okay, so if the velocity error is high, you're gonna get a stick instead of a carrot. This is 0.1, it could be increased, and of course you want to penalize if the acceleration of the car, of the ego car, is too high. You don't want to do things too abrupt, so you also give a stick for that. Okay, so everything is summed and you have the reward in here, the overall reward. Okay, now finally that's, you got the observation, you got the reward, but also you have the Easton flag. This means that in order to train the reinforcement learning agent, you're gonna do a lot of experiments, and sometimes the experiments can go really bad. For example, you crash your car with the one in the front, or your car stops. You want the car to stop. So that's precisely the two rules that we have for the Boolean. So if your relative distance is less than 0, it means that you crash with the car in the front. If your velocity of the ego car is less than 0, it means that you stopped, and you don't want that either. Either of the two are gonna stop the experiment. Okay, now we understand the model, so let's do the reinforcement learning agent. Let's gonna create it and train it. Okay, so let's go back here. Okay, so yeah, we have the model. We're gonna use a set of functions from the reinforcement learning toolbox from MATLAB, and in this set of functions, the functions need to be aware of what are the observations and what are the actions that the system is going to take. And for that, we have this RL numeric spec, so we can specify for the actions and observations, we can specify either continuous variables or finite variable with finite values. So in this case, both of them are continuous. Okay, so the observation is going to be a vector of 3 elements we specified in here, and the lower limit is negative infinity and positive infinity for both of them, so really there's no bounds for them. Okay, so let's create this. And now for the action, we also create a reinforcement learning numeric spec, and it's only going to be a scalar. And as mentioned before, it's going to be bounded between -3 and 2. And also notice that in here for the action, we have a saturation block, and it uses the A max ego, A min ego, which is going to limit to -3, from -3 to +2. So that saturation is going to limit the action as well. But we also have to tell the reinforcement learning libraries the limits. So that's why we have this. And now we're going to create the environment. The environment is the model name that we just saw, the block of the reinforcement learning agent, which is basically the path to this block, the observation information, and the action information, and we're going to have the environment. And again, as mentioned before, sometimes the experiments for training go astray, and we have to reset the environment. For example, when this is done, is true, then we have to invoke a reset function, and that's why we provide here is basically a callback. You can define any function in there. In this case, it's very simple. I'm not gonna debug through it. It's just gonna set a variable in the model, which is the initial position of the lead card. It's gonna set it to a random value. Okay. So now, since there's randomization involved, we want to make this predictable by setting the generator seed to default. Now let's create the neural networks for predicting the long-term reward of the agent. Okay, so first, the agent is gonna have two parts. One of them is the critic that is gonna predict the long-term reward, and then you have the actor, which is gonna take the next action. Okay, so let's go to the critic first, and the critic is gonna take as inputs the observation, but also the previous action. And we're gonna use fully connected layers. These are fully connected layers are powerful, but also expensive computationally, and especially if you have 4 straight fully connected layers, as you see here. Although the network looks small, the computational cost is way higher than a convolutional neural network, which basically has a small window weight. But these are basically huge weights. It's like matrix multiplication, all these combinations. So it's gonna you expect to have a large training time because of that, but still it's powerful. And usually these examples from reinforcement learning are using fully connected layers. There's also a rectified linear unit to create that non-linearity, and we have an addition layer that is going to connect the path of observation and the path of action. Yeah, so we have the path of observation. The fully connected layers are going to use 48 neurons for each one of them, and then we add both of the paths to the critic, and finally the output of the action path is going to be connected to a second input of the addition layer. Okay, so now let's take a look to the critic network, and as we saw, there's some branching. The fully connected layers, every one of them has 48 with 3 inputs here, 1 scalar for the action, and finally we have the output reward, which is a scalar. Okay, so now we have the critic network. We're going to specify the options for the critic, which are some training parameters. For example, L2 regularization factor, a gradient threshold to avoid the gradient from exploding, and learning rate, 1 to the negative 3. And with that, we have the observation information, we have the action information, which are the numeric specification that we have in here for the action and observation. We have to specify also the input name observation from the layers, and the action, which is the input of the action, and also the options that we just created here. And finally the network in here that we created. With that, we have the critic. And now we need to create the actor. The actor is going to be similar. We're going to have a simpler network, which takes as input the 3 elements of the observation, fully connected layers, and finally we put a tangent, a layer that is going to limit the output values, and then we scale it and bias it so that the outputs are between -3 and +2. Okay, so we have the actor network. Again, we specify a smaller learning rate than the other, and the rest of the parameters are the same. Again, we pass the same observation info and same action info, and we have to indicate the input observation, but in this case the action, instead of being an input, is going to be the output of the network, and we have to put the name of the layer in here. We pass the action options, and we pass the actor network, and now we have the actor. With both of them, now we can create the agent finally. The agent has some options as well: the sample time, smooth factor, discount factor, mini batch, etc. So, and also some noise options. Okay, now we have the actor, we have the critic. The actor again is gonna determine the action. It's a neural network that determines the action. The critic is the neural network that determines the long-term reward and the options. And with that, we got our agent. And now we're gonna train it. And for training, we have to specify training option, maximum episodes. We're gonna say 5,000 steps are gonna be sample time divided, final time divided by sample time, which is 600, and no verbosity. And also we have to indicate when to stop. At the beginning, the reward is going to be very low, and eventually, as the networks get better, it's going to increase the reward. And well, the example determined that the acceptable reward is going to be 260, so that's where it's going to stop. So we indicate the stopping criteria is going to be the episode reward, and the stopping value is 260. Okay, so now we have the training options. So now with the agent, the environment, and the training options, we're gonna be able to train the network. This is gonna take a long time, so eventually it's gonna look like this. It's gonna be start very low, and eventually it's gonna get into a good reward, and it's gonna predict correctly the long-term reward. I'm gonna stop this eventually and load the pre-trained network. So, but I'm gonna show a little bit how it looks. It is kind of interesting to see how the initial experiments are pretty bad. Eventually the agent gets good, and I'm gonna show it. You can see that this is the distance, and the safe distance is yellow and the relative distance is blue. You want the relative distance to be above the safe distance. So if you see the relative distance drop down to 0, if it goes to here, the blue goes here, it means that the car is crashing. And you can see at the beginning it's crashing all the time. But not only that, but also it's not meeting the target velocity. The target velocity is the yellow, and blue is the velocity of the ego vehicle. You want the velocity of the car to be the same as yellow, and you can see no way, it's accelerating too much. So it's basically, yeah. So it's not stopping because of the velocity getting to 0. It's stopping because it's crashing. So you can see acceleration is kind of crazy. He doesn't know what he's doing yet. But eventually, if you leave this training for a long time, then eventually it's gonna get better. Okay, so you can see here that the score is pretty bad. Eventually it's gonna get good, and you can see that there's a lot of time to go, but I'm not gonna go through it. I'm gonna stop the training. Gonna close this, and instead I'm gonna load the pre-trained agent, and I'm gonna do, well, I can do it through this API, but I'm just gonna run the agent in the model. I'm gonna show you the model. Notice that now the model doesn't look red because we have the agent. So yeah, let's take a look. Information overlay, dimensions. Yeah, you can see here that the observation is a vector of array of 3 elements, and this is a scalar boolean, etc. So we're gonna simulate this. We're gonna take a look. Okay, I'm gonna put the other windows in here. Okay, so we have the model in here. The agent is already trained. So now let's just run it to see how good it does. Okay, let's run it again. Yeah, maybe I'm gonna try another thing. Okay, let's try it again. Okay, well, it is not perfect, but I think it's doing a good job because the relative distance is about 30 feet. It could do better. And as mentioned before, if you want to improve this, the way that you program the reinforcement learning is by changing the rules, changing the sticks and the carrots, which is happens in here. Notice that the velocity of the car does very well getting adapted to the desired velocity. But what happened here at the beginning, you have the car that is way below the desired velocity, and also it's at a safe distance at the beginning, so it's gonna only take care of getting into the desired velocity, so it's gonna accelerate. But then at this point, even it has not arrived, the velocity of the car in front is gonna start accelerating. So I guess he's still okay, and eventually gets to the desired velocity. But what happens here is that the car in the front starts going down in velocity, so it's getting closer to you. So the safe distance is gonna decrease. And now at that point, it's gonna use a negative acceleration. So it's gonna brake, and then by braking, it starts to improve the relative distance. But this doesn't improve it that much. And then again, once the front vehicle gets to a higher velocity, now it's safer, so it is free to accelerate again to get the desired velocity, which is achieved in here. But still, this can be improved. Let me see if I can get back the control of the model. Yeah, this can be improved in the reward formula. You can notice in here that the error velocity is 0.1. This can be incremented to maybe 1. That's one option. But also the way that the relative velocity is determined. This is kind of suspicious in here. If your relative velocity is bad, you should not only, not use this one, but use a smaller velocity or something smaller, so that you can go below faster. So yeah, that's a couple of things, but in the end, this is where you program the reinforcement learning, and I found it quite intuitive and easy to do. Yeah, so basically that's it. Thank you for watching.